Hello, everyone. Welcome to my talk. In this talk, I will talk about the Cubature method for rough volatility models. This is a joint work with Feng at USC. So let's first look at the option pricing problem. Given the stock price ST, we want to compute the expectation of G of S capital T under the winner measure P. Roughly speaking, the Cubature method is the way to find the so-called Cubature measure so that we can numerically compute the option pricing problem. The general idea follows from the Taylor expansion. Let's consider the stochastic differential equation is in the Straightanovic integral form. Then G of S capital T by the change of a variable formula has the following forms. So this is the first order, and this is the second order. So those will be some constant depends on the function G and their derivatives. If we further take the expectation and the winner measure of this function, then eventually, except for those constant C1 and C2, only matters for us is the expectation of the iterated integral against the Brownian motion under the winner measure. That means for the Cubature measure Q, we want to find the expectation of the iterated integral against the Brownian motion under the winner measure Q here, okay, which we want this to be easy for computation. If we go one more step, the Cubature formula that was introduced by Lyons and Victor can be think of in this way: that for each of the expectation of different order of the iterated integral of the Brownian motion, of course, this is in the Straightanovic sense, is just the summation of the weight lambda I with the integration against the deterministic path omega I. Okay, so in this way, the Cubature measure is constructed by using the weights lambda I and the delta measure on the path of omega I. So this way, we have a discrete approximation of the winner measure P. The omega i's are the deterministic paths, and the lambda I are the weights, which will construct a winner measure, Cubature measure we want here. Indeed, the iterated integral of a Brownian motion is the signature of the Brownian motion in rough path theory. So these are some general related works. The problem for us is that if we consider that xt is not Markovian, for example, we want to consider the rough Hessian model. The stock price ST is still driven by a Brownian motion. However, the volatility will be driven by a Volterra type SDE. So this is not Markovian anymore, and the option pricing problem U of t, the path of x, will solve the so-called path-dependent PDE, not the parabolic PDE as we see before. So how do we compute the expectation and the winner measure of this function? Of course, the standard Euler scheme works here, but not efficient. So our main comparison for today's talk would be the efficiency between this Euler scheme for under the Monte Carlo simulation and our Cubature method. So in general, we consider this type Volterra SDE. This general Volterra SDE will cover the rough Hessian model. So for presentation convenience, I will only take the one-dimensional SDE, where is xt here. So for example, this xt is not a semi-martingale because of the parameter t here. So how do we compute this winner measure expectation against this Cubature measure? Of course, the technique I introduced before for the Brownian motion will not work in this case. So the general idea still follows from the Taylor expansion. However, we need to introduce some tricks. If we introduce a two-parameter process, theta st, then you see that for fixed time parameter s, theta t will be a martingale. Then this technique can help us to do the Taylor expansion as we did before for the Brownian motion case. And this trick has been first used by Vince and John, and then later on recently by Harrer and Tino. In the first order, this will just give us the integration against the Brownian motion with the kernel involved. And we further do the Taylor expansion of this product will give us the second order expansion. That's the second term here. Eventually, we will also have this constant that depends on the function and their derivatives, and then the iterated integral against the Brownian motion with the kernel involved. So those will be the terms that we want to match by the Cubature measure. For example, in the order 3 case, we will want to pick the path omega with their anti-symmetric path, so that the sum of these two integration will be 0. So the only even order term will contribute to the expectation of this iterated integral. For example, if we pick a kernel has this t minus s to the power h minus half, then the expectation of iterated integral against the Brownian motion in the Stratonowicz sense can be computed explicitly. And if we pick further that omega are linear, piecewise linear functions, then those two equations can be written down explicitly, and we can find the path slope for the omega. In the one-dimensional case, if we want to consider order 4, then we are going to have 24 equations. And for two-dimensional case, order 4, we have 42 equations. So the higher order Cubature formula will require more equations to solve for us. The general algorithm follows the 3 steps. First, for a given order, we need to solve the equations, which I just showed you. In the order 3 case, we have 2 equations to solve. To solve the ODE is the second step, which means, of course, this is a special ODE. However, the omega are deterministic paths. By using the Euler scheme, we can find the terminal value of x tilde. Then, to compute the option pricing problem, this is just the summation of the lambda I and plug in g of x tilde with the value we computed from step 2. So this Cubature measure indeed does not depends on the function g. So this is very flexible, very convenient for our computation for general options. So this is an example for order 3, where we have 2 equations and we can find precisely a and b at the slope of the linear piecewise function. So in this case, the Cubature measure is constructed by a, b, and lambda 1, lambda 2. In general, if we consider order 4, then we need to solve the equation both satisfies order 2 and order 4, and also for the weight lambda. So that in total, we'll have 24 plus 2 plus 1 equations. In this case, we will consider the optimization problem, which is non-convex with constraint. The constraint comes from the weight of the measure. Then we found the path. The first one will be the omega 1 up to omega 9, and then this will be plotted with the anti-symmetric path. With this path, we have the Cubature measure. Then we want to compute the Monte Carlo simulation solution and the Cubature solution. And then we want to show the efficiency in the Cubature solution sense. First example, let's take time t is 0.5, sigma is a constant 1, option function is cosine. Then at the same accuracy level, the Cubature solution running time is around 6 milliseconds. However, this one is around 20 or 21 milliseconds. Okay. Now let's look at another example. Let's say, okay, we still pick sigma to be 1, but we pick t to be 0.2. Okay. Now let's look at the cosine function first. In this case, at the same accuracy level, the simulation solution should run 238 milliseconds. However, the Cubature solution only takes around 6 milliseconds. So the running time is very efficient for the Cubature solution. They are around the same accuracy level. Similarly, x squared, the running time for the simulation solution will be 115, and the Cubature is 5.22 milliseconds. For the option function, for the co-option function, this is not differentiable at the x equals 1/2. And then in this case, the performance is a little slow in the sense that the Cubature simulation solution will have running time 14 milliseconds, and they will have around the same accuracy level. In general, we also test on the sensitivity on optimization errors, because when we use the machine learning package to solve the path, we need to lower to make the loss function to be smaller, and then we have the sensitivity on that one. We also test on different time scales, like time scales here, and also different combination like sigma is not a constant and other option functions. We also test on different h, where of course we require h is bigger than 1/2, because we want to consider Streetonowitz integral here. So here is another example, that is the rough Hessian model. In this case, is a 2-dimensional case, okay? With t will be 3-dimensional, and this is the path by using the machine learning package we found, and these are the anti-symmetric paths. In this case, we have the numerical results. We take t is 0.1, and the sigmas are the functions I write down here. Let's look at the call option function here first. Instead of having them at the same accuracy level, we now to look at the Cubature solution and compare it with the simulation solution. Namely, the running time for the Cubature solution will be 568 milliseconds. And for this accuracy, it's around 8 percentile for the simulation solution, which means 92% of the simulation solution will not perform as good as our Cubature solution. And the running time will around 4 seconds. So for the cosine function here, similarly, the accuracy for the Cubature solution will be around 8.72 percentile around the true solution. And the running time for the simulation will be 4 seconds, and this is for the 600 milliseconds. For x squared, something similar here. The accuracy is around 12 percentile accuracy. Okay, so we have other test functions. We have different sigma, sigma-1, and drift functions in the paper. Okay, so thanks for your attention. So this paper is in preparation and will be on arXiv soon.